Hey all, so we are going to spend this entire week working through optimization problems from 4.7. So just giving you that, there's my oven, giving you that heads up. So you're going to have three very small problem sets from 4.7 to work through, but they're all word problems, so they take a little bit longer, and I do want you to do the additional practice plus the presentation problem. So from my perspective, it makes sense to just give you time to work through all of those. So get yourself ready for notes and we're going to get started. So the first thing I want to talk about is what does the word optimization mean? So as I said, these are all going to be optimization problems. And the idea is in trying to optimize something, you want to find the most, you want to find the least, you want to find the closest, farthest. You could make up any of these sort of words, but that's the sign that it's going to be an optimization problem. So you're going to find the most, the least, the closest, the farthest, the biggest, the smallest in a situation. So that situation might be a word problem, it might be a math problem. And whenever you see a problem like that, the goal is just to find the min or the max, depending on which of these words. Obviously, if it's most, you're finding a max. If it's least, you're finding a min, etc. Of the function of the situation. So you're going to write the function, reduce the variables as needed, and then find the min and max, which again is where 0 is equal to that first derivative. So those are your skills that you're going to do. Now, today's problem sets are going to be about area problems, then we'll do volume, and we'll do distance. So, a gardener wants to put a fence around a vegetable patch in her yard. One side will be the wooden fence that's already up, and the other three sides she'll make from 18 yards of chain link that she has. What is the maximum area of the vegetable fence the vegetable patch she can fence? So, what I will often do with any sort of geometry type problems is draw a quick picture out first. So if she already has a fence up, doesn't have an arrow, it's a solid fence, and she's going to put in a vegetable patch, and she only needs to fence three sides because one side's going to be against the fence. So we've got a length, and then a width of the patch, and this green part is made up by 18 feet of chain link. So this is the given information. Now, we know it's an optimization problem because it's asking, oh, what is the biggest area of the vegetable patch? Now, what this tells us is that the function of our situation is going to be the area of this rectangle. And then the question is going to be, I'm looking for the maximum there. Now, so the function would be length times width. Now the first thing we want to do is reduce variables, because whenever we take the derivative, we take it as d blank of the function. And if I have one variable in this function, I can just put that variable in here, such as x. But if there's 2, 3, 4, I have to use implicit differentiation. It becomes a whole thing. So my goal here is to reduce the variables, and this is going to be true in all of these. There's going to be some sort of specific given, such as we see here, and that'll allow us to say, for example, in this case, oh, well then 18 feet is equal to 2 lengths plus a width, and so that's how I can reduce my variables, which means that one width is equal to 18 minus 2 lengths. And so when I reduce the variable here, I can, so that it's only in terms of L. So now I have area is equal to L times 18 minus 2L, which is 18L plus 2L squared. And this is what I mean by reduce variables. Here we had length and width as two variables. Now we just have length, so that means that I can take the derivative in terms of that single variable L. So then a prime, the derivative of that function right here, is equal to the derivative of 18L plus 2L squared, which is 18, whoop, I've been putting a plus in, my apologies, minus 4L like so. Since I'm trying to find the maximum, I'm going to set that derivative equal to 0. So 0 is equal to 18 minus 4L, and I'm just going to solve for L. Therefore, 4L is equal to 18, L is equal to 4.5. The unit that we were given here is feet. Sorry if you can hear my dog having little zoomies in the background here. She is almost 7 years old, and there's no excuse. Now, since it asks for the dimensions and for the maximum area, so the question was, what is the area that maximizes this? So it's great that we found that this length here, this length maximizes it. So the maximum area, as we saw before, is 18L minus 2L squared. So if I want to find the maximum area, I'll just plug that number in. 18 times 4.5 minus 2 times 4.5 squared. Plug that in and I get 40.5. The unit is feet squared. So this is one example using area. You're going to see 2 more examples throughout your notes, one with volume tomorrow, and then on Thursday, one with distance. If you have any questions, please let me know, and I'm happy to help you work through any and all problems in this set, either on Zoom or nominate them, and I'll make some videos.